Сейчас я еще раз позову, потому что... Vamos. Okay, so this second part of the lectures by Dmitry Melnikov on nodes and all that.
Okay, thank you, Sasha. Okay, so yesterday we discussed some technical material which allows us to consider these diagrams of nodes and compute some numbers for them, and I hope that you got the idea. And mainly you need to remember that for any diagram with closed lines, we can associate a number, or actually in this case we'll have a polynomial. And also we had braids that appeared in the discussion, right, something like this. And I was kind of hinting that this kind of diagrams with open lines, they also look like operators. So today we'll try to relate this to more explicitly to quantum mechanics, and we'll try to build quantum mechanics based on nodes. So this is the plan for the lecture today. At the end of the lecture I mentioned Chern-Simons theory, so as an example of a topological theory, and the topological theory was defined as a theory whose Lagrangian is metric independent, and today I'll give another definition, a more general, and it's actually based on category theory. I'll just introduce the very basics of category theory at the level that you can really enjoy it. And so then I will use this general definition to settle a final model that would be used in all my computations. And I call it topological quantum mechanics, but because it will be an example of a one-dimensional TQFT, but it will actually be based on Chern-Simons. So it will be the same as Chern-Simons. So I will use this model to discuss, introduce, and start the discussion of quantum entanglement. But first I want to give some additional material that I didn't manage to mention yesterday, and this is also some background that is kind of motivational background which will explain certain statements that I will make in the following. Okay, so as I said, we discussed the Chern-Simons was introduced. So this is a slide from yesterday, and again, this is the Lagrangian, the action, and the equation of motion, which tells that field theory is just the strength of field strength is 0, and the configurations are pure gauges. So I want to talk a little bit about quantization, how Hilbert spaces of these theories are obtained, and it is the most simple to quantize Chern-Simons theory on three-dimensional manifolds which have this structure. So there are two-dimensional, well, in this case, Riemann surface sigma times a circle. And there was actually a question yesterday how you compute nodes and whether you can compute invariants in different manifolds, not only in R3, or actually what we discussed was a three-dimensional sphere. So this will be an example of such a calculation. Okay, so you can go to Coulomb gauge, for example, and in this gauge the action simplifies a lot. You just get actually a free theory action which you can easily quantize, but what you have to remember that the theory has a Gauss constraint. So there is a constraint due to this gauge fixing, and this constraint is actually this requirement that, well, in this case, the component 1, 2 of the field tensor is vanishing. So you need to impose this constraint, and this constraint, what it does, actually eliminates a lot of degrees of freedom of your theory. So you start from this, well, seemingly free theory, which is standard free quantum field theory. You try to quantize it, but then constraint kills almost everything. So basically it leaves only 1 degree of freedom, and even more than that, from this 1 degree of freedom, there is only a finite number energy levels that are left. And the exact number, the exact dimension of the Hilbert space. So what I wanted to say, the Hilbert space is actually finite dimensional, like a two-state model or n-state model, n-level model, and so on. So the number of the dimension of the Hilbert space will depend on the topology of this two-dimensional surface sigma. So let's discuss sphere and torus in particular. So what we want to understand, we can start first imposing this constraint at the classical level and try to understand what are the really degrees of freedom and physical degrees of freedom in the phase space. And as I mentioned yesterday, so the traces of the Wilson loops, they are the most generic gauge invariant observables, and you can study those. And if you do this for a sphere, then actually on a sphere, because the theory is topological, there are really no independent degrees of freedom. So everything reduces to a trivial monodromy. So any kind of loop that you can draw on a sphere is contractible in a sense. And this corresponds to the very trivial Hilbert space. So the Hilbert space will, after you quantize, will contain only one vector, which is the vacuum. On the other hand, if you look at the torus, there are some non-trivial monodromies on a torus. So you can just take a Wilson line which winds around non-trivial cycles of the torus. And then you can do it several times in one direction. And then, well, in fact, the ends here on the quantum level, the number of independent degrees of freedom will be also limited by the parameter k. So at the dimension of the Hilbert space, so the number of independent degrees of freedom will be k plus 1. And the formula for generic genus surface, two-dimensional surface, is given by this formula. So again, so what I want to say here is that after quantizing the Chern-Simons on this space like Riemann surface time a circle, you will get a finite dimensional system. And in fact, so your gauge constraint kills almost everything. So you started with something which was seemingly a quantum field theory, but you actually ended up with finite dimensional quantum mechanics. So we can do, so far sphere is the most trivial example. The dimension of the Hilbert space was 1, but what you can do to cure the situation for the sphere, you can add particles, as I also mentioned last time. So you can think of it as some single gauge transformation which introduces delta functions in the field tensor. And then you can consider monodromies that correspond to loops around these charges, the particles. So if we're talking about abelian case, these are charges. And if we're talking about non-abelian case, what replaces charges in this case are irreducible representations of the gauge group. And then when you discuss monodromies, then you should, on a closed space, you should remember, if you consider a trivial loop on the closed space, but there are some charges, then the calculation, which doesn't enclose any charges, so you can have a sphere with some charges, and then you consider Wilson loop, and you can, which does not have any charges inside, so it is a contractible loop, so it should be trivial. Yeah, sorry. But this should be equal to the monodromy. So you can also think of this circle as enclosing all the charges together. So there should be this consistency condition. The result of computing this monodromy should be the same, and which means that the sum of all charges should be 0. So this would be the abelian statement, or in a non-abelian statement, all representations, the tensor product of all representation should be trivial, so it should be a singlet. So you have this additional constraint So put this in different ways. So the problem you'll need to solve, you'll associate an irreducible representation to every fixed point. You look at the tensor product of these representations, and you need to count how many singlet representations there are in a tensor product. So a little bit more. So if we're discussing the SU2 case, the reducible representations, they're just spins. So you're just looking for a state whose total spin is 0. And a slight generalization of this is just you look at something which is called fusion algebra. This is a little bit more general than just the rules of adding angular momentum in quantum mechanics. You just take a tensor product of representations, you expand it in the sum of irreducible representations, and what happens in Chern-Simons that this is not in general the tensor product of spins, but it is representations of quantum groups. And in this case, these multiplicities in particular, they can vanish even though they do not vanish for regular tensor representations of spin. So which means that the actual number of singlet representations may be smaller than naively expected from the spin quantum rules, from the tensor product of spin representations in usual quantum mechanics. So here is the summary. If you have a sphere with no particles inserted, so 0 charges, in this case, as was said, the dimension of the associated Hilbert space is 1, it's trivial. If you put just one charge, obviously one charge, you cannot form a single with just single charge, so the only possibility to insert this charge, it already has to be in a singlet representation, it should be a singlet. If you put 2 particles, so to make a singlet, well, let's think again about of SU2. In SU2, you take any spin, but then you can form a singlet from 2 representations of the same spin. So you have this delta R1, R2. So this is the only non-trivial case. For 3 particles, the dimension of these fusion numbers, or exactly these numbers that appear in the fusion algebra. These are multiplicities of the irreducible representations in expansion. So if it's SU2, that this can be only 1 or 0. These numbers are either 0 or 1, which basically this number measures how many, by fusing or considering a tensor product of 2 representations, let's say spin 1 and spin 2, what is the possible what is the possible spin that can be formed in this tensor product? So if we are talking about J1 and J2, then 2 spins, then the sum of the spins can vary from J1 minus J2 absolute value to J1 plus J2. Yeah. I'm not sure what is inside the manifold and outside. Or you mean, so we're on the surface of the sphere. So this is, we're in 2-dimensional space and it's closed. Do you mean you want to put the particle here? Yeah, so again, so in this case, there's the same consistency condition on the monodromy. So here, if you have 1 particle, you have a certain monodromy, and this should be equal to the monodromy computed if you consider this loop as encircling all the remaining charges, which means that the total spin, again, if we're in SU2, then the total spin of all these particles should be equal to the spin of this particle inside. Okay. So you can continue this table. And next I would like to just mention how you use this to compute the simple partition functions of Chern-Simons theory. So you want, let's say, compute the partition function or path integral of Chern-Simons theory in this manifold, sigma times S1. So here in this picture, you have this sigma as the Riemann surface, and then you just start evolving this Riemann surface in time, and then when you want to compute, so if you compute it on sigma cross S1, it means that you at some point you just close your evolution and you have a picture like this. This is not a true picture because I cannot draw this three-dimensional space. So this is kind of lower dimensional illustration of this manifold sigma times S1. And this is analogous to computation of the finite temperature partition function, where the time is periodic, Euclidean time is periodic. Well, note that Chern-Simons theory is a topological theory. The difference between Minkowski and Euclidean is just one sign in the metric, but the theory is independent of the metric, so it really doesn't care whether the theory is Minkowski or Euclidean. And also, because it's topological, the Hamiltonian of this theory is 0, so which means that the evolution operator is just identity operator. So in this case, you can think of this picture here as time evolution of the surface, but nothing happens with this Riemann surface along the evolution. So again, evolution operator is identity operator. So this picture should correspond to basically computing a trace of the identity operator. Okay, so that's the same thing. And the trace of the identity operator is just the dimension of the Hilbert space. And how to compute the dimension of the Hilbert space, I just tried to explain, right? So if we have a sphere, for example, then the dimension of the Hilbert space associated with the sphere is 1, and we'll compute the trace of this Hilbert, of the identity operator on this Hilbert space will be just 1. This also applies to the case of the sphere with charges. So in this case, if you just think of the manifold in which the lines are not doing anything, they just continue with this time flow, and then you consider this cylinder and you close it on itself, computing the trace, then again you're computing the trace of the identity operator, but now the dimension will depend on the number of the particles that you insert and on the spin of the particles. But you can also think of a more general situation where these lines actually do something, and what they can do, they can braid, form. This picture, for example, appears in the discussion of anyons and quantum Hall effect and so on. So you can assume that something happened to the lines. So it is not the evolution of the Chern-Simons theory itself, but it is kind of some kind of external operation that you can apply on these charges. You can move them around in your quantum Hall experiment. And then if you close the cylinder with this braid inside, what you will compute is the trace of this operator that realizes this diffeomorphism. So this no, you can still think of, well, yeah, so what will happen in this case, the topological theory, the equations of motion of Chern-Simons is F equals 0, right? You have, but then you can have F equals to to be a sum of delta functions, right? So, which means strictly speaking, it is not 0. There are certain points where it is infinite. So whether you should call it topological or not, it's a matter of taste, I think, but so I think it is still largely topological, but you have these additional particles. So it is the simplest example of Chern-Simons with matter, which you mostly retain all the topological properties, but Chern-Simons Hamiltonian itself cannot generate any evolution because it's trivial. So apart from Hamiltonian, you should assume there are some other operators. Or you can start with your theory as theory with no Hamiltonian, but then you have some set of, I don't know, quantum gates, some unitary operations, and then you say, now I will, you have some quantum computer, you have certain gates, and you say, I will build my own Hamiltonian from this set of gates that I have, set of operations. This will not be, probably should not call it topological theory, but it's something you can build on top of Chern-Simons theory. Well, this is actually computing traces of braids, right? This is something we did last time. We discussed matrix representations of braids, and then we discussed computing traces. One question that appeared last time was whether computing just trace of a braid will give topological invariance, and I introduced a special trace which was called Markov trace, which guaranteed that if you compute it on your braid group representation, it gives you a topological invariant. So connected to what discussed yesterday, so if we just, let's focus on SU2 theory, and our charges will be just fundamental representation, spin 1/2, and then if I just look at this diagram, right, in terms of the representations that I considered yesterday, so each line is a two-dimensional representation, so it's really like a spin 1/2 particle. I consider just 4 lines, and I compute the trace of this operator that just should compute the dimension of the Hilbert space of 4 spin 1/2 particles, which is 16. But I said that to be a topological invariance, you have to compute Markov trace. So according to the rules given yesterday, if I compute the Markov trace, if I just draw a diagram with the closure of 4 parallel lines, what Markov trace must compute is the Jones polynomials, but in this case, as I said, I will just associate a number to any closed loop which is not entangled with anything. So this should give me just 4 factors of D. So how do we compute this trace that was shown in the previous picture, in the previous slide, right? When you have a cylinder and you close the cylinder. So I said that, well, I haven't said this yet, but for, let's say, 4 spin 1/2 particles, we expect the dimension to be 2, and I will explain it a bit later. So I want a trace that will compute this identity operator and give 2 instead of 16, or instead of this d to the 4. And for that, we'll need to introduce some operators. It will be clear, hopefully, in the discussion which will follow, how to define as appropriate operators that will give the dimension of the Hilbert space. So in principle, with this, you should be able to compute any Jones polynomials or analogs of Jones polynomials on any 3-dimensional manifold, closed 3-dimensional manifold. Okay, so these were some additional comments to yesterday's lecture, and now I move to the next topic. So I'll need to introduce a TQFT model based on certain set of axioms, and this set of axioms use category theory. So I'll just give very basic introduction to category theory. So category theory is the idea of category theory that you want to discuss different structures that appear in mathematics and find relations with them, so that I suppose if you're able to prove certain theorems between for some set of structures, you can just use the category theory and export these theorems just directly to different mathematical structures. So here I will give some examples of kind of structures that will appear in topological quantum field theories. But in principle, every category consists of objects, A, B, and C in this diagram, and a set of arrows between objects, which are called morphisms. So you have a map from A to B. I also have maps from A to A, and the axioms just say that these arrows, they should have a composition. So if I have a map from A to B and a map from B to C, then there should be a composition that maps from A to C. And there should be an identity morphism, which maps any object to itself, and it also composition it with any morphism gives the same morphism. And this composition should be associative. And the very basic example, which is very familiar to us, is just vector spaces. So you can think of vector spaces of arbitrary dimensions. That will be this ABC. And linear maps between these vector spaces will be these morphisms. So matrices, which these matrices can map this space, one object, one space to itself, or they can map between different spaces. So these matrices are not necessarily square matrices and so on. So these are category of vector spaces. And the other category that I will use are called cobordism categories. So what is cobordisms? So objects here will be some oriented compact surfaces sigma with certain dimension D, and morphism will be just higher dimensional manifolds whose boundaries are these lower dimensional, whose boundaries are manifolds sigma, so the objects. So here's an example. If I look at any of the parts of this diagram, here I have two disks, and which are two-dimensional objects, and there is a three-dimensional space which connects two disks. So this is an example of a cobordism. And the composition of the morphisms will mean that I should be able to glue the different cylinders in this diagram. So here, for example, this when two cylinders have a boundary of the same type, it means that I have one morphism whose image is a certain object, and the other one has its domain in the same object. So which allows me to glue two cylinders together. And there is identity cylinder, so that's the most simple space that bounds the same type of an object, the same type of sigma, and it does nothing. So it is sigma times basically the unit interval. Okay, so there are categories, and there are maps between categories. So categories, they have certain maps within themselves. These are called morphisms, but you can also have maps between different categories, and this is what we'll be interested in. And these maps are called functors. So functors are just maps that preserve the structure of the category. In particular, they're supposed to map objects to objects, and they also have to identify the morphism. So they should preserve the structure of the arrows in every category. And then they should, they should map identity morphism to identity morphism. They should, that's basically, the second statement here is just a statement that the functor preserves the morphism, and then it should also preserve the composition of the morphisms. So now the definition, topological quantum field theory is a functor from a category of cobordisms to category of vector spaces. So I told you that cobordisms are those manifolds that connect different manifolds, lower dimensional manifolds. So the topological quantum field theory will be a map from this kind of structure to linear spaces. And here is the more explicit construction. So this functor will take a d-1 dimensional surface sigma and map it to certain linear space. And this linear space we'll later understand as the Hilbert space. And then if you take go to one dimension higher, so d-dimensional manifold M, whose boundary sigma will be mapped to a vector, and this vector in the image of the manifold of the manifold sigma. So higher dimensional manifold will be mapped to a vector in the Hilbert space. So if you have two sigmas, and then you have a manifold that connects them, a cobordism, so that will be mapped to a linear map between two Hilbert spaces. So here is just a diagram that illustrates these definitions. on the left is an illustration of a vector. So you have certain space sigma, and then you glue a higher dimensional object to the sigma, and this will be the vector. So sigma is something which tells you, well, what kind of boundaries these higher dimensional manifolds can have. So you can have different higher dimensional topologies, but they will have the same type of boundary, the same sigma. So it means that the sigma is universal for all vectors, and in the same sense as Hilbert space is the is something that's the union of all vectors. So that's a set of all vectors psi. So here the second example is the example of an operator that is applied on a state in this Hilbert space. So again, here's a manifold which is mapped to a state by the TQFT functor, and here is an operator that acts. So it's a manifold, but now this manifold has an additional boundary, and the property of this manifold that is can be glued to the state and produce a new state. The TQFT functor will have to satisfy a set of additional axioms. I will not be very precise, just will mention some most important ones. So if you have a manifold which has no boundary, so this should be mapped to a zero-dimensional Hilbert space. So zero-dimensional Hilbert space is just C, the complex numbers, or a single point. And this allows us to define a scalar product. So if you have two states with the same type of boundary, so the vectors in the same Hilbert space, you can just glue them together, and this will produce a Hilbert space, as this diagram here shows. Well, the identity will be just a trivial cylinder. It's a trivial evolution of a surface sigma. And another important property is that if you have your boundary has disconnected components, so this sigma is a union of two disconnected components, sigma 1 and sigma 2, then the functor will map it into tensor products of linear spaces, of tensor products of Hilbert spaces. Okay, so we have an example, which is Chern-Simons theory. So in this sense, the functor is actually given by the path integral. And in fact, the whole idea of defining topological quantum field theory as in terms of category theory, in terms of some functor between different categories, came from this property of the path integral. So initially, topological theories were defined in quantum field theory as a certain theories with an action, but if you compute the path integral is not well defined mathematically. So Michael Atiyah, who formulated these axioms of topological quantum field theory, proposed another definition which would not concern mathematicians that much, but it is consistent with all properties of the path integral. In particular, so if we just start with the Chern-Simons theory, and we can compute the state in this theory as a path integral, where you just take the integral of all configuration with fixed boundary conditions on a given Cauchy slice. So you can again think of this theory in sigma times S1. So S1 is your time, you fix certain time moment, and you fix boundary conditions on the sigma, and you compute path integral over all configurations with these fixed boundary conditions on the surface sigma. So this should produce a state in the Hilbert space. And then you can just take two states like this and glue them together and integrate over boundary conditions, and this will be analogous to gluing two manifolds in the axiomatic formulation. So here in this formula which defines a state, you can see this explicit map from M and sigma. So you have M, which is a manifold where you compute, where this action is defined. So it is a manifold which has a boundary sigma. So this path integral computes you a map from M and sigma to a certain to a vector in certain Hilbert space. Okay, any questions so far? Okay, so now we'll do a reset, and I will define the model which I will use for my computations based on well, some definitions and the general story which I've presented so far. In particular, what I want to define is a one-dimensional TQFT. So TQFT, which will be okay. Actually, there's one more thing that I wanted to, a few more comments that I want to make. So I will just work with SU2 Chern-Simons theory, and this SU2 as a boundary, the sigma will most of the time use two-dimensional spheres, S2. And these two-dimensional spheres will be non-overlapping, which means that in general the states that I will consider, there will be states in this Hilbert space which are Hilbert spaces associated with spheres and spheres with punctures. So some examples here, this is a 3-ball is the most trivial state. The most trivial example of a 3 manifold whose boundary is a sphere. Or you can have a sphere with 2 boundaries, and in this case the theory is defined in terms of the filling of the space between 2 spheres. Or here, for example, a 3-ball with 2 cavities. This is an example of a Hilbert space or a state in a Hilbert space defined for 3 spheres. So as I mentioned before, so for just regular sphere, the Hilbert space has dimension 1, and if you want something non-trivial, you need to introduce charges, which means you have to remove points from the sphere. So this is in some way repeating of what I discussed before. So if we put particles in the fundamental representations of SU2, so what I need to calculate if I want to define the dimension of the Hilbert space is to compute how many trivial representations, singlet representations that appear in a tensor product of spins of all particles. And here is an example for 4 particles in spin 1/2. So this is particle physics like notations. You have products of 4 doublets, 4 spin 1/2 particles, and then you expand it in sum of irreducible representations. We'll have spin 3/2. You'll have a triplet of spin 1 and 2 singlets if you just compute this expansion of this tensor product. So which means that if I put 4 particles on a sphere, the dimension will be 2 because there are 2 singlets that appear in this tensor, in the expansion of this tensor product. So in this case, the dimension of the Hilbert space is 2. And one way of seeing this, I can take now think of this path integral in the 3-ball with whose boundary is a 2-sphere which has 4 punctures, 4 charges on the sphere. Well, in the volume of this 3-ball, these punctures, charges should be connected by the lines, the Wilson lines, and then the fact that every Wilson line should start and end in a charge, you can interpret that as producing a singlet. So here, for example, the line connecting these 2 points means that the 2 points, the 2 charges are in the total singlet state. These 2 here are also in a singlet state. So this will be an example of a state in this 2-dimensional Hilbert space. But you can also use an alternative way of connecting particles. So this is like a different fusion channel. So you just first fuse particle, let's say 1 and 4, and here 2 and 3. So that's an alternative way which will produce an alternative state. But these 2 states are not orthogonal, but you can find an orthogonal state by using Gram-Schmidt procedure, by just subtracting the state 0 with certain coefficient, and then you compute the scalar product and require that this is vanishing. So this story is more about regular SU2K, but we'll work with regular SU2 representations, but we'll work with quantum group. So there will be fusion algebra. We'll work with fusion algebra of SU2 K West-Zumino-Witten theory, which is equivalent. So the action of Chern-Simons theory can be written in terms of action, a boundary action, when we consider Chern-Simons theory with the boundary, and this action is known as the West-Zumino-Witten theory. And quantizing this theory, we'll find that the basic operators of this theory, they are classified by the representations of SU2, but only finite number of representations appear. And this number depends on K. So in principle, as I mentioned earlier, for certain values of K, you may have that these tensor products produce less singlets than expected from just regular tensor products of SU2 representations. This is an example of computing a scalar product for this kind of states. So you just take two examples that I showed on the previous slide, and you glue these 2-3 balls over their two sphere boundary. So what you should produce in this case is just a closed loop, and this which space this closed loop will live in. So just the answer will be just S3, and this is, you can think of this as a definition of S3. So S3 is a compact closed space, and if you draw a sphere in S3, then you will have the interior of the sphere will be a 3-ball, right? So this is what we know as the 3-ball. But the exterior will also be a 3-ball. So this is what the difference between R3 and S3. So S3 is basically consists of 2 3-balls glued together. So the scalar product will be a line, in this case just a trivial loop, but can be something more complicated in S3. So then the expectation value, this overlap of two states will be just a computation of the expectation value of the Wilson loop operator, or just the Jones polynomial in S3. But if you consider states, some other examples of states, for example, a state which is defined in the Hilbert space associated with two spheres, right? So you can think of, you compute your path integral of Chern-Simons theory in a space which is bounded by two spheres. Then when you will compute the scalar product of two such states, right? So you can think of, well, just take two such states. So you need to glue the interior and the exteriors. So if that would be a two-dimensional example, what you would get a surface of a two torus, right? Unlike the example of two disks. So if you have just two disks, if you just glue two disks along the circle boundary, you'll get a sphere. So in high dimension, 3 dimensions, what you'll get is a manifold which is S2 cross S1 when you glue these two spheres with cavities. So that's a different way of drawing. This is a more heuristic representation. You have this state. At the bottom, you have a state with two S2 boundaries. And on the top, you just take another state of the same kind and you glue. And you see that as a result, you'll get a manifold with a hole inside. So it's a manifold different from S3. In this particular example, you have every sphere has 4 punctures, so it's a 2-dimensional Hilbert space, and there's another 2-dimensional Hilbert space. So you have a state in the tensor product of two-dimensional Hilbert spaces. And then you can compute this partition function using the basic observation that I made a bit earlier. So this particular example looks like an identity operator, which you compute in the Hilbert, whose trace you compute in the Hilbert space of dimension defined by these representations R1, R2, R3, R4. Okay, so now I go to the one-dimensional TQFT, the definition of one-dimensional TQFT, which I will work with. So in the one-dimensional TQFT, you start with, so Hilbert space will correspond to surfaces sigma of dimension 0. So it has to be dimension 1 less than the dimension of the TQFT, which are just points. So I'll consider a collection of points and I associate this Hilbert space, these points to certain Hilbert space. So what are the vectors in this Hilbert space? I'll just consider, I need to glue one-dimensional manifolds to these points, so that points are the boundaries of this manifold. So I just consider open lines that connect the different points. So if I just consider this without any additional restrictions, I will probably get some trivial TQFT. But I will just tell that it will matter to me not only which point connects to which, but also I will say that there's certain order, there's certain interactions of this connection. So the lines will somewhat know that, well, they can link with each other. And you can understand this in terms of maybe one-dimensional spin chains. You have spins which can interact. So here, this horizontal lines, they're just time evolution. So 2 points in the middle, at some point, they interact. This crossing is a certain type of interaction. Here is again the same type of interaction. Here is, you can think of some kind of annihilation of two particles that occurred in the stereo and so on. So I can see these diagrams as sort of evolution of particles, or I can think of this diagram as another way, in a different direction. So at a certain moment of time, I had the creation of two particle-antiparticle pairs, and then some of them got interacted, and the result of this history, I got some state in my Hilbert space. So to compute linear, to compute inner products, scalar products in this Hilbert space, I'll have to first define how I compute the complex conjugation or Hermitian conjugations of the state. Well, the trick is basically to define this state so that it's compatible with unitarity. And for that, if I just take this state, it is better if I define the Hermitian conjugate in such a way that my evolution basically goes in the opposite direction, which in this case means that I do some kind of mirror reflection of my state. Mirror reflection, one thing it does, it just changes overcrossings and undercrossings, and it will also change the order of operations in time. So for scalar product, I can take two states, and if they're in the same Hilbert space, which means they correspond to the same number of points, I can just glue the two states along these points. So the result will be something which has no ends, so it's a number, and this number is, the trick is that this number, I'll require that it is basically Jones polynomial. So for that, I will just need to also define the dimension of this Hilbert space, and I will require that the basis states in this Hilbert space will be constructed with all diagrams which have lines with no intersections. I will call it temporally Lieb basis because yesterday I defined temporally Lieb algebra. So the states will, temporally Lieb algebra has this property that the generators and all elements, they are represented by lines which do not have intersections. So this is the generator. If I just bend it and draw this diagram like this, so this will be a basis state in my vector space. So I do something like this. I just connect it like this, or maybe the other way around. Or I can think of the identity in a temporally Lieb algebra and bend it, and this will make a state like this. Yes? There should be R3? Yeah, so implicitly, in the previous slide, right? So implicitly, my theory will know, well, it is certainly, it requires me to think of three-dimensional space, right? So it is best to think that these lines exist in three-dimensional space. So that's actually the idea of holography. Holography is the following. You do something two-dimensional, but then at some point you realize that somehow to express what happens in 2 dimensions or on any dimension, you need an additional dimension. So if you just add an additional dimension, it will be easier for you to explain certain things, right? So for this particular, I just told you that what I have here is, certain type of interactions of particles in 0 + 1 dimension. I can just, instead of drawing a diagram, I can give some explicit matrix. But this matrix will have certain properties. They will probably satisfy some braiding relation, Young-Baxter. And then I just realized, oh, I can use maybe some higher dimensional pictures to just draw this diagram. So this is what holography does, basically. That's the most primitive way of seeing what holography is. So the coordinate here is these lines. So the copordism can also connect, let's say, certain manifold and a closed and an empty manifold. Empty manifold is just a point, right? So that's also copordism. So that, in my case, the boundaries are just sets of points. Yeah. So you just think of these are high dimensional pictures. What this will be when the boundaries are just 0 dimensional. You just need to consider a set of lines and whose boundaries are points. Yeah. Okay. Yeah. So I just basically use the axiomatic definition to tell you that I will have 0-dimensional boundaries and 1-dimensional points. In principle, you can also check whether all other axioms of TQFT are satisfied, but they are more or less satisfied by definition, by construction. But then I impose additional requirements on my TQFT because I do not want to consider all possible 1-dimensional TQFTs, but very specific ones, and I want this TQFT to be compatible with knot theory in such a way that all expectation values, all overlap scalar products of states in my Hilbert spaces will be computed by Jones polynomials. So I just told you that I want to restrict so far the definition was implied some kind of infinite dimensional Hilbert spaces, but now I tell you that no, I just look at all my states should be expanded in certain bases, and in particular, this choice can be a basis. And for that to be compatible, I need to have linear relations between states, and this linear relation will be provided by the skein relation that I introduced yesterday. So if you have a state with intersection, it just means that it is a linear combinations of states without any intersection. So in this SU2 theory, of course, the number of points should be even because you cannot form a singlet with an odd number of spin 1/2 particles. And you can also compute, like for a given number n of points or 2n, what will be number of diagrams of this type that you can draw, and this number is given by the Catalan numbers. So that's also the dimension of the temporal Lieb algebra. So if you have So if n is 0, no points, you have a one-dimensional Hilbert space. If n is 2, you have 2 points, you have a one-dimensional Hilbert space. If you have 4 points, you have two-dimensional Hilbert space. And for 6 points, you have 5, right? For 8, 14, and so on, and so on. But this is a naive calculation because, again, there's one important point that we're not working with just normal SU2 spins, but we're working with representations of a quantum group. So there'll be, in general, certain restrictions, which means that in sometimes when you fuse particles with spin J and spin J1 and J2, the result will not necessarily produce J1 plus J2 because depending on the number K, J1 plus J2 may exist or may exist or not in the theory. And we actually do not need to know this, these properties of Wess-Zumino-Witten theory. We can discover it in this construction. Well, the two states that I presented as a basis, they are not actually orthogonal. So you can compute here in the middle, you have the diagram that should compute the overlap of the two. And in my theory, I said I want this to be computed by John's polynomials. And as I explained you last time, this actually should give me a number d, right? So here, this kind of overlap gives d squared. This one also gives d squared. So this basis is not orthogonal, so I need to use again Gram-Schmidt procedure to orthogonalize that. That's again something I mentioned before. Well, you normalize it, you orthonormalize it, and you can also compute all the overlaps, all the coefficients in these definitions if you just use the set of rules that I introduced last time. So for any separate circle, I will introduce factor of d, and I'll use scaling relation for any diagrams which have intersection to simplify them, to reduce them to linear combinations of diagrams without intersections. And okay, remember these properties that D and A are related via this relation. So given the basis, you can compute the Gram matrix, and the Gram matrix will tell you whether it's a good basis, right? Whether all the states, all the vectors in this basis are linearly independent. So if you do this for just this two-dimensional space which I just described, you'll see that it is the determinant of this Gram matrix is d squared times d squared minus 1, which tells you that when d is 1 or d is 0, you actually get a degenerate basis. And that's the example of this effect of quantum group, that for certain values of d, and remember that d and k, they are related. So d is related to a, and a is related to k. So a is a phase, exponential of e, I, pi, and here divided by 2, k plus 2. So if I put k equals 1, this will produce exactly d equals 1, and then I'll get degenerate basis, which means that the two diagrams that I showed you, they are no longer independent, they just represent the same vector. So this is just a reflection of the fact if you look at the Wess-Zumino-Witten theory with k equals 1, you will only have one you will only have one primary operator in this state, in this theory. So if you just go to k equals 2, then there will be no problem. Or actually, if k is not integer, you'll never have a problem. But for k equals 2, it is good. My basis is good enough. You can work with it. But if you go to a state which is based on 6 points, and you compute the determinant. So as I said before, this is Hilbert space of dimension 5. Again, you'll find a degeneracy for certain values of k. In this case, for k equals 2. So if you do not want to have degeneracy, you better work with either non-integer k or maybe very large k. So very large k is the so-called semi-classical limit of Chern-Simons theory. Okay. Well, and so one observation, so this is basically my construction of quantum mechanics, one-dimensional TQFT, but it's actually the same as SU2K Chern-Simons theory, and I just gave you example how you can learn something about Chern-Simons theory by just playing with this one-dimensional diagrams, right? Just this computation, for example, knows about connection of Chern-Simons theory and Wessel-Minowitten theory. So here again, there are a couple of examples of states in this construction. So this is the state in this one-dimensional TQFT, and it is, you can understand it as an analog of this kind of state of Chern-Simons theory, which we define in three-dimensional space with S2 boundaries. So it's a 3-ball with 4 punctures. You can connect these punctures by Wilson lines, and well, this map is not unique, but it is defined up to some unitary transformation that moves the points around the sphere on the left-hand side. So whenever, in the future, whenever I write this line is just analog of this boundary two-sphere in Chern-Simons theory, which just show that, you know, four points here, they just join together to form a Hilbert space. Here's an example of a state in a tensor product of 2 such Hilbert spaces. Well, it's certainly not an accident because I wanted it to be this way, right? Whether this, I think the fact that this works is a bit non-trivial, but I mean, I cannot explain more than that. Okay, so now I go to the next topic, which is quantum entanglement, and I will use these definitions to basically to explain what quantum entanglement is and discuss its properties. So just a quick, very basic reminder about quantum entanglement. So if you look at the multipartite system, which means you have a system with the tensor products of Hilbert spaces, and you have a state in such a Hilbert space, then if it's a pure state, right? So you can take it and produce a density matrix by just considering a square of the vector, and then you can define something called the reduced density matrix. For example, if you want to just effectively work with subsystem 1, you can compute the partial trace with respect to all the other subsystems, which means that you take density matrix and you sum of all indices which correspond to subsystem 2, 3, and so on. Then, if the result will be some matrix which you can also write as a product, as a square of some vector, then this state is, we call such a state separable. But this is not always possible. So if your reduced density matrix is not a product of any couple of vectors, then you say that your system H1 is entangled, is in an entangled state. And the most famous example or set of examples are the so-called EPR pair or Bell states, right? So the classic property of this state is that if you collapse or project on any of the 2 spins, you will immediately know the state of the other spin. And so this property of knowing about the other subsystem by doing measurements on one particular subsystem is a form of correlation, and a measure of this correlation is called entanglement. One of the measures, you can introduce different measures, but one most common one is von Neumann entropy, and this is computed in terms of density matrices. So if you have a bipartite system, A and B, you can compute density matrix for one of the subsystems and compute this trace of rho log rho, compute the negative of that is called the von Neumann entropy or entanglement entropy. And one simple way, well, useful trick to compute this entropy, because it involves logarithm of matrices, is called the replica trick. So in the replica trick, you compute not the logarithm of the matrix, but in certain cases it's easier to compute the powers of the matrix, integer powers. Then you compute the trace of this integer power, you compute log. This is called the Rayleigh entropies with this particular normalization. And then you take the limit n going to 1. Then this will give you if you do proper analytical continuation, that this gives you trace of rho log rho. And for the example of the Bell state on the previous slide, the reduced density matrix is diagonal with 1/2 on the diagonal, and you can, if you never did this with replica trick, it's probably useful exercise. Well, just compute any power of this diagonal matrix. It's very easy, right? And then you compute log of the trace of that and take the limit n going to 1. The result will be log of 2. So this is the situation, particular situation, but one of the problems for quantum information is to understand what kind of entanglement of what kind of correlation exists and try to classify them. And this problem is solved for bipartite systems, but with multipartite systems, it is an open question. So how to properly classify different types of correlations. So in this lectures, I will try to give certain view on how you can understand different types of entanglement, and I will use topology for that. Well, one classification that exists in quantum information theory is called classification by stochastic local operations and classical communication. I'll try to explain what this means using topological language. So this SLOC classification is wants to classify different entangled states in terms of the action of local operations. So let's assume you have different subsystems and you have local operations, so which means operations that can only act on these subsystems, but not on, let's say, any pair or any union of the subsystems. So the most general operations are just SLN, and you can classify states, but just taking, the most general set of state, which is just the tensor product of C to the n1 and 2 and so on, the dimension of the Hilbert spaces, and divide this by the tensor product of all local non-unitaries, all local operations, invertible operations. So if you do this for 2 qubits, you'll find that this quotient actually is just a set of 2 points, and this corresponds to 2 classes. One is called separable, and the other one is called Bell class. So which is basically tells you that for 2 qubits, they can be either in the separable state or in an entangled state. If you just consider a general bipartite system that is product of tensor product of Hilbert spaces of dimension m and n, then there will be the number of different types of entanglement according to this classification will be equal to the smallest number of this pair m and n. Well, so for 3 qubits, you can also apply this classification. Again, you'll find a finite answer. There will be 4 classes, either separable or the generalization of the Bell class when 2 of the qubits will be in an entangled state and the third one will be not entangled with the other 2. And the 2 classes of genuine 3-partite entanglement, one is called GHZ and the other one is called W, and later I will explain you what they are. Well, if you go further, if you look at 3 Q-treats, they correspond to Hilbert space of dimension 3 or 4 qubits. In this case, there is no finite classification. There are infinite number of classes, and some partial classifications exist in this case. So now I will, how do you do classification in the bipartite case? It's actually quite simple exercise. You just do a Schmidt decomposition of your density matrix, of the reduced density matrix, and you count the number of non-zero coefficients. So you can always write any matrix in this form. With certain positive, non-negative coefficients. Some of these coefficients might be 0, and you count the number of these non-negative coefficients, and this will different numbers, 1, 2, 3, will define which class the state belongs to. Well, one observation is that if you apply local unitary operations, they will not do anything to entanglement. And in fact, for Neumann entropy, preserve this entanglement. But what can change the amount of entanglement are local invertible, general invertible operations, which are not unitary. So if you just try to look at the, let's say, start with 2 qubits, which are in an entangled state, and apply local invertible operations, in general, if you start from maximum entanglement, this type of operations will reduce the amount of entanglement. But they will not take you from, since they are invertible, you will never produce a separable state. So different invertible operations, they act within each of these law classes, mapping states with more entanglement to states with less entanglement. So there's one result which I want to mention in this business is that if you have these local operations which are invertible, so they correspond to certain stochastic or classical protocols. So they are not quantum in the sense that you are not applying unitary, because local unitary cannot change the amount of entanglement. But what these classical or stochastic protocols can do, they can always produce, if you start with a state with certain amount of entanglement, they can always produce you a state with less entanglement with probability 100%. But you can also try to go in the opposite direction and start with a state with less entanglement and produce a state with more entanglement. And with this kind of operation, you can only do this stochastically, which means that you will only have a finite probability of success for this kind of operation. Okay, so these were just an overview of results in quantum information. Now I will want to go to topology, and some kind of early ideas of relating topology and quantum mechanics and entanglement was this. People refer to the paper, to some proceedings of Aravind at 97, who suggested the following, which is quite natural idea, right? Because links is something which have entanglement, but classical entanglement, topological entanglement. Why don't use links to classify the quantum entanglement? And the proposal was the following. So if you look at just a bipartite state of 2 qubits, it is natural to associate a Hopf link to an EPR state. And if you understand measurement as collapsing any of the circle, then the other example, which is the GHZ state, so here's the explicit form of the GHZ state. So the suggestion was let's consider these Borromean rings. So Borromean rings have this property: if you remove any of the circles, so measurement means collapsing, removing a circle, collapsing a state. The result, if you remove any of the circles, the other two will be disconnected. You can easily convince yourself that this is the property of this diagram. And this is also a property of the GHZ state. If you measure any of the qubits, then the remaining two will find themselves in a separable state. So that was the proposal, but it was a bit too naive. And so here I'll talk about the different proposal, which was appeared in different forms for different kind of topological quantum field theories, but obviously topological quantum field theory is the right language which associates topology with quantum states in the sense of these axioms of Atiyah, which I reviewed earlier. So what does the entanglement means in terms of topology? So if you want, in fact, the way the Dirac notations for the vectors in Hilbert space are already kind of suggest of how you should think of the topological realization of these separable states and non-separable states. So the product of psi and psi, or the tensor product of two states, as I said, should correspond to, well, if you look, obviously should be separable in terms of, okay, in terms of this diagram. So you'll have a state in the tensor product of two Hilbert spaces, each associated with two surfaces sigmas, and if you draw the state such that the topology, the higher dimension topology, do not connect the two boundaries, then that should be a separable state. But if you have a topology which connects the two boundaries, that this obviously looks like something non-separable and entangled. So the situation is a bit more tricky. In fact, the separability of this diagram, which is so far just a very heuristic diagram, depends really on what the dimension of the space associated with sigma left and sigma right. And in certain cases, you can just simply have a trivial Hilbert space associated with it. So even though there is something which looks like a space, there might be not entanglement between the two sides. So in general, you need to have something, you might need something additional elements like Wilson lines connecting different surfaces to guarantee entanglement between the subsystems. And this is, of course, reminds us about all these discussions, popular discussions in the last decade about emergence of space from entanglement, right? So what does what space is? Well, space is actually, again, if you think of holography in such a way, it's a useful tool for you to think of certain properties of your lower dimensional theory. So I need this additional dimension just to tell that, you know, my subsystem A and B are entangled. So there's space that connects to them. So that's again this ER equals APR, another form of introducing that. And well, we can use now the replica trick and try to discuss and try to check explicitly the entanglement entropy for the two states and check that indeed the one is entangled and the other one is not. So how do we do replica trick? Right, we need to compute density matrix, we need to compute reduced density matrix, and we need to compute the powers of the reduced density matrix, and then analytically compute trace, analytically continue, and so on. Okay, so this is how we compute the density matrices, right? This is the left state, the right state. The density matrices are just the duplication of the state, and I write one upside down just to show that I also apply Hermitian conjugation on the state. Then I want to compute partial density matrices. For that I need to do partial trace. So what does it mean computing partial trace in this case? Well, I need to, partial trace is the operation where I just identify indices with two Hilbert spaces and sum over that, which is like a multiplication, and multiplication is just gluing spaces. For example, if I want to compute trace over subsystem B, I just need to glue sigma B and sigma B conjugated. So the result for the density matrices, for the left one is just this diagram here, and the other one is just a cylinder. So if I connect sigma B and sigma bar here, the space topologically will just be this cylinder. Here I also normalize them. So for normalization, I need to further compute the trace. And in this case, if I compute the trace, I need to close the cylinder, and the result will be, well, if sigma is 2 sphere, the result will be S2 cross S1, or in general, it will be sigma times S1. In this case, the trace of that will be this kind of melon or watermelon that is drawn here, and I need to divide it because it's a normalization factor. Okay. Then I need to compute nth power and compute the trace. So for the first example, in fact, for both of them, if I compute any power, so in this case, when I compute the power of the cylinder, right, I just put one cylinder on top of the other, but gluing two cylinders together produce another cylinder. So this part, which is this topological space, does not change. The only thing that changes for this example is the power of the normalization factor. In the second case, when I glue the two together, I put one on top of the other, the product will produce another melon, which will cancel one of the normalization factors. So for the second example, any power of this density matrix will be exactly the same thing. So, which means that when I compute the trace, since my state is normalized, I just get 1 in this example. And in this case, I'll get this, again, the same thing as the normalization factor, but this normalization factor will be computed at power 1 minus n. And then I do analytical continuation. I can either compute divide by 1 minus n, take the limit n going to 1, or I can compute the derivative. So in the first case, of course, the result is 0. The state was separable. In the second case, the entropy is the log of the donut. And the donut, as we learned, is a trace of the identity matrix. So if the state, okay, this was actually some heuristic state. I didn't tell you what exactly inside this topology. But if this topology looks like an identity operator, so it has some kind of translation symmetry. If you go from one to another, then you'll just compute the dimension of the Hilbert space, and that's an example of a maximally entangled state. Yeah, so for the state that we discussed before, if I put 4 punctures, there will be 2-dimensional space, and if it's an identity operator, then you'll get log 2. Okay, I'm not sure, maybe I should stop at this moment, and I'll start this topological classification. Well, let me maybe flash few examples, just not to forget the things I said about quantum information theory. So if I want a separable state, and I consider a product of 2 Hilbert spaces, so I have this left sphere, right sphere. If I want something separable, my lines should not connect left and right, right? That's an example of a separable state. If I just if I just connect the 2 boundaries by lines which do nothing, which looks like an identity operator, I will get a maximally entangled state. I can also apply local unitaries. So in my picture, any braiding operation of any braiding of lines will be a unitary operations. So this is also a maximally entangled state. So if I want something which is not maximally entangled, I need to apply something which is not a local unitary. So this operation here, because I do a braiding again, but this braiding is non-local in the sense that to create this kind of state, I have to exchange lines points between left and right. So that's a non-local braiding, and it produces something which is not maximally entangled. So that's an example of non-maximally entangled state. This is some illustration of why braiding is a unitary operation. So you can just take one state and compute it complex conjugate, which is, as I said, you basically invert the evolution. And if you glue them together, well, this by construction, you'll see that the operations you do on this on one non-conjugated piece will basically exactly cancel by operations on the conjugated piece, and the result will be an identity matrix. While in the second case with this non-local braiding, you see that if you just glue the state and its conjugate, then obviously this is not an identity matrix because you cannot undo this loop in the middle. Okay. And just a reminder, if you do not have a connection between left and right, this will be a projection, because this is actually, you can recognize here, these are temporary leap generators, and as I introduced them last time, they are projectors. So they have some zero eigenvalues. Okay, so tomorrow I'll start with this part. I told you at some point that there is this property that if you have non-unitary invertible operations, that they convert different types of states between each other, but you can produce states with less entanglement with 100% probability, but in the opposite direction you can only succeed with finite probability. Okay, so I think I'll stop here.
Okay, thank you. Questions?
Before you were using the Wilson loops to calculate or to extract some Jones polynomial that essentially is some not invariant. I don't get the distinction that you can have from this case from another that's just a trivial line operator. The case of these Wilson loops, how they are conceptually different, maybe.
So sorry, I don't think I understood the question.
Because you can have Wilson loops in a trivial case, just a line operator, or in this case you are doing to extract not invariant. Conceptually, which difference I can have in these cases?
So, okay, I need some help to understand the question. So, I can compute. I can consider, well, the simplest example of a state, a bipartite state, right, is something like this, which I said is an identity operator, and I can compute this exactly using the basis that I showed you before. So how do I compute that? So I have one basis state which is like this. So I actually, up to normalization, I said that's the state 0. So I glue this state on the left, and I glue this state on the right. So I get something with no open ends. So I just tell this. I want to associate a Jones polynomial to that. So I just need to use the rules that I introduced before. So what kind of Jones polynomials that is? This is a Jones polynomial of two closed circles, which is d squared. So this d squared, which is basically the coefficient of the state 0, 0. Then you need to compute 0, 1 and 1, 0. Well, 1 is a bit tricky because 1 is a linear combination. You have to glue a linear combination of the diagrams. One is like this. The other one is the same as before. Well, you have to divide by some normalization factor. Actually, you will see in this case that if you put 0 on one side and you glue 1 on the other side, that you'll get 0. So this state, if you compute all 4 cases, you'll just see that this is 0, 0 plus 1, 1. So this is indeed equivalent to an identity operator. Okay? So every time I will glue state on basis state on one side and a basis state on the other side, well, not basis state, but this basic non-orthogonal diagrams that also form a basis, I get some knot, and I use rules to compute the Jones polynomial. So I'm not sure what is the other case that you referred to that.
Like when you're doing Wilson loops for a trivial line operator.
Trivial. Yeah. So you wanted to see what is the difference between, let's say, the cylinder which we close, right? So that, and then we want to compute something like this. So we want to close the cylinder on itself, and this will produce 4 loops in the space which is S2 cross S1. How do you do in this picture? Well, you need to, technical answer to this question, you have your state, which in this case you can think of, okay, it's an expansion in the basis, right? So if you want to compute the trace of that, you need to compute trace of this matrix of coefficients. But what is trace of matrix of coefficients? Is just the sum ICJ, right? So I can think of this matrix of coefficients is equivalent to the operator. It's equivalent to a matrix which defines the state is this matrix. So I just need to compute the sum of 0, 0 coefficient and 1, 1 coefficient. They're both 1, so the result will be 2. And I think I'll need to make this comment tomorrow also, just to formalize this kind of computation of the trace, right? So I said that I'll have to basically introduce some projections in my matrix representation to be able to compute, but that's the projections will be defined in terms of these diagrams as like this. So just this projector which I mentioned in the beginning of the lecture will be just, well, 0, 0 in terms of topological diagram plus 1, 1.
More questions? Okay, so let's thank again.
Oh yeah, so there is also homework problems, by the way. Actually, I did almost did the first exercise. Yeah. So what you need to do is do this exercise by gluing ones and check that, for example, mixed coefficients 0, 1, 1, 0, they vanish.